Hello everyone, welcome back to another remote sensing lecture video. And in this lecture video, what I want to talk about are the idea of indices. So indices, as we've mentioned multiple times, are just basically an equation involving one or more bands. So we've actually kind of seen an example of a very basic index when we talked about ratios, but we sort of give them their own name because they're sort of an important enough subclass of indice, and they're so sort of generic and basic that they just get their own name of band ratio. But technically, they are an index. But indices typically will go a couple steps beyond in terms of complexity. Now they're not, normally they're not so complex that they're requiring, matrix algebra or something like that to understand. Generally, they're just some combination of addition, subtraction, multiplication, and division, right? They're basic arithmetic, typically. But the nice thing about indices, and I said this in a previous video, is that they often have a specific purpose. Right, which also means they often have a specific interpretation. Right, so if you remember back to the end of our discussion on band ratios, I said that one of the key sort of cons to using band ratios is that being able to have any concept of whether or not a large number was actually large depended on the underlying data. What the radiometric resolution was, what those pixel values actually meant, right? Because 16-bit radiance is going to mean something very different than 8-bit reflection in terms of the maximum value that you would expect a pixel value to have, which is in turn going to affect the maximum value you would expect the band ratio to have. So conceptually, they were really simple, but interpretation-wise, they tended to fall apart pretty quickly. Indices, on the other hand, they're made for a specific purpose, and they usually have a very specific range of values and a very specific interpretation of those values. So what I want to do in this video is I want to talk about one of the most common indices that you are going to come across in remote sensing. And it's actually going to sort of involve those same bands that we talked about with the band ratio example that we went through. And what I want to talk about in this case is what's called normalized difference vegetation index. Or you will often see it called NDVI, Normalized Difference Vegetation Index, NDVI. And so what I want to do is I want to go through and quickly just talk about the equation and where the different parts of the name come from. So index, right, is because it's indice. Right, it's an index. Let me clean that up a little bit. Right, it's an index, right? It's one of these things that we've called an indice. Vegetation, because its purpose is vegetation, right? The specific purpose of NDVI revolves around the idea of vegetation. So it's an index with the purpose of vegetation. Difference, because bands are being, that was terrible, bands are being subtracted, as we'll see in just a minute. And then normalized, because we're doing what's called normalization, which means we're making the values range between 0 and 1. or sorry, not 0 and 1, between -1 and 1. All right, so normalized values range between -1 and 1. Difference because the equation is going to involve subtraction. Vegetation because the specific purpose is for vegetation. And then index because it's an indice. So even the name here is extremely indicative of what we're trying to do. So let's talk about the equation, NDVI. So NDVI is NIR minus red over NIR, not MIR, over NIR plus red, right? This is it, right? This is the index. So like I said, it's a little more complicated than a band ratio, but we're still not talking about calculus here, right? It's basic arithmetic, subtraction, addition, and division. So what I want to do is I want to talk about what these values can sort of range from. So let's think about one extreme where NIR is as high as it's going to be and red is as low as it's going to be, right? So if red becomes negligible, right, if this reduces to 0, then some large number minus 0. Actually, let's write this out, right? When NIR is really, really, really large and red is approximately 0, right? Red is as low as it's going to go. What happens? Well, this equation simplifies to NIR, right, plus 0 over NIR minus 0, which means you get NIR over NIR, and anytime you divide a number by itself, you get 1, right? So when NIR is as big as it's going to get, this equation goes to 1. So we have an upper bound, right? No matter what data we put in here, whether it's 16-bit, 28-bit, 37-bit, whatever number of bits we want, no matter what we do, the maximum value of NDVI is always going to be 1. So let's go through and talk about what happens when NIR is equal to red. Okay, what happens in that case? Well, let's go through this, right? In this case, right, what does this boil down to? Well, when NIR is equal to red, we say the top, right, becomes NIR minus, right? So NIR is equal to red, which means I can just put another NIR here because they're equal to each other, over NIR plus NIR, right? So when you subtract something from itself, this goes to 0, and this goes to 2 NIR. So what happens when we take 0 and we try and divide it? Well, this is going to go to 0. Right? So when NIR and red are close together, these values are going to converge to 0. Let's talk about one last example. Right? When red is far greater than NIR. So this is saying when NIR is really, when NIR basically is approximately 0 and red is really, really, really big. What's going to happen to this equation? Well, let me just quickly do this again down here. Right, we have NIR minus red over NIR plus red, right? This is just reiterating that equation from up there. Well, what happens when NIR goes to 0? We have 0 minus red over 0 plus red. So now this is going to become, right, negative red over red. When you have a negative something divided by a positive of the same thing, right, that's going to become -1, right? And so when red is really big and NIR goes to 0, right, this equation tends towards -1. So this normalized equation now has an upper bound of 1 when the two values are, when the red and near infrared are approximately the same, it tends to 0. And when red becomes significantly large and NIR goes to 0, the low value is -1. So I'm going to repeat that one last time. And I'm actually going to write it down. Right, NIR ranges from -1 when red is far greater than NIR, to 1 when NIR is far greater than red and tends to 0 when NIR equals red. Right. So what we've done here is we've kind of gone through the same logical approach that we took with the band ratio. What are the extreme values and what happens when they start to converge? And we can see here that with the band ratio, right, it skyrocketed up to some unknown value that was dependent on the data. With NDVI, now we've constrained that, and we have a very specific set of numbers between -1 and 1. And we have a very specific interpretation of what those numbers mean. So hopefully this makes sense. I know there was a lot. I encourage you to pause the video, go back, rewatch the part you're confused about. And as always, please reach out. Thank you.